Alright, what's up everybody? So, we are into 10.4, which is technically area of regular polygons and also area of two-dimensional compound figures, but this video is only going to focus on area of regular polygons. And I will say this is probably the most involved lesson, so thinking caps on. If you haven't printed out the outline, I would highly recommend printing out the outline for this section. Okay, so let's get into it. Regular polygons. So remember, polygons have to have straight edges. They never crisscross. Nothing's rounded. Okay, triangle, polygon, quadrilateral, etc. Those are polygons. Octagon, hexagon, etc. But a regular polygon is a figure where all sides are congruent and all of the interior angles are congruent. Okay? So something like this, right? So this would be a regular pentagon. It has 5 sides. All five sides are congruent, and we would also know that all these interior angles would be congruent as well. But we don't need those marked down just yet. Okay? So I'm going to put this in a circle, and the reason why I'm going to put this in a circle is because we're going to talk about central angles here in a second. Okay, so even though I drew a circle around this pentagon, all the diagrams that you guys are going to be looking at won't have this circle. The circle is just for reference. But it's also important to note that if a polygon is regular, it can fit inside a circle that's the correct size, and every vertex of your polygon will be on the circle's edge. Okay, that's true for a triangle, it's true for a square, it's true for a regular octagon or a heptagon or a hexagon. Okay, if the figure is regular, you're able to draw a perfect circle around it, and each point of your polygon will be on the circle's edge. So that's important to remember. Okay, so the circle for this diagram and the pentagon have the exact same center. Okay, so if I was to draw a radius here or here, they're all the same length. Okay? Like such. So notice what I've done here now is I've drawn 2 radii, and they're creating this arc for this circle. But it's also sectioning off this part of our pentagon, in this case one of the 5 sides. But it's also making a triangle. Okay? The 2 radii combined with the side of the pentagon is making that triangle in yellow. Now it's also important to note that this central angle is going to be the same as this arc measure. Alright? Another important thing to point out is that notice how many arcs we have. 1, 2, 3, 4, 5. Notice how many sides we have for our pentagon. Also 5. So the number of arcs created is also the number of the same of sides that are within your shape. So now if I add in 3 more radii, okay, so 1, 2, 3, notice how many triangles I have. 1, 2, 3, 4, 5. I have 5 triangles, the same number of sides that I have. How many central angles do I have? 1, 2, 3, 4, 5. What do all 5 central angles add up to be? 360. Because we have 5 arcs. Notice how it's kind of all tying together. Okay, the arc measures, the central angles, the regular pentagon. Right? So all the triangles are isosceles. So that's important to know. We know that all of these radii, because these are all radii of our circle. So all 5 of those radii are the same length, making every single triangle within our pentagon isosceles. Remember, isosceles means 2 sides are the same length. The number of triangles is equal to the number of sides, and that'll be true for any polygon. So if it's an octagon, a regular octagon that's 8 sides, that means if I was to do this type of drawing, there would be 8 triangles inside my figure. If I was doing a hexagon, 6 sides, there'd be 6 triangles inside my figure. Okay? All the triangles are congruent, meaning every single triangle right here is all the same size. Okay? If we can find the area of one triangle, then we technically can find the area of our entire figure. So if I found the area of this, all I would have to do is multiply it by 5, because there's 5 of them. All right? So let's pull one of those triangles out. Okay, so I'm going to pull out that purple shaded triangle, and I drew it dotted, and notice that we have isosceles markings here. So let's think about this. What do we need to be able to find the area of a triangle? Let's think back to our formula, right? We need the base, okay? So that base length right here is the same length as this right here in red, okay? We also need the height, and that height, let's pick a good color that's going to jump out at us. Here is be the same distance right here in orange, okay? So those are the two measurements we would need to be able to find the area of one of our triangles in our regular pentagon. So the height of the triangle, or the distance from the edge, the middle of a side of a regular polygon to the center, is called the apothem. A-P-O-T-H-E-M. Okay? So again, if we're just looking at a triangle, we call it the height. But if I'm looking at this figure as a whole, this regular pentagon, the distance from the center to the edge that is perpendicular is called the apothem. Okay? So the apothem is perpendicular to the side of the polygon and connects to the center of that side, as well as the center of the... So this right here, it's also dividing up these two sides in half. Because remember, the altitude, aka the height of an isosceles triangle, cuts it in half. That's important to remember. So, things we know so far. We know that the area of a triangle is 1/2 base times height. Okay? We know that this black segment going from the center of our pentagon straight down to the edge. So pretty much, guys, it's the shortest distance to the edge of our figure is called the apothem. Okay? So all I did is I just took all the notes and I just moved it to the next slide. So we're pretty much picking up exactly where we left off, so you don't have to copy any of this down, because you should already have it. So we can find the area of our regular pentagon if we had the base length, we had the height length, and we had the number of triangles. Okay? If we had all that information, if I knew, for example, if I knew what this orange was and I knew what this orange was, I could just plug those numbers in, and in this case I'd multiply it by 5 because I have 5 triangles. However, there's an easier solution to this. The base times the number of triangles is actually the perimeter of our figure, right? So if I have my base length, if I was to multiply that by 5, that would give me the distance all the way around my regular pentagon. 5 triangles, 5 bases. Okay? And the height of our triangle, as we already said, is the apothem of our pentagon. So how can we simplify this formula? So what's going to happen is the area of our regular polygon formula, and this doesn't matter how many sides it has. It could be used for a triangle. It could be used for a decagon. It can be used for a hexagon. Is 1/2 times the apothem times the perimeter of your figure. So it's the apothem of your polygon. It's the perimeter of your polygon. Okay? So the thing, if I was to make a regular pentagon again. The two things I would need to know to be able to find the area of this figure would, number one, be the apothem, and then number two would be a side length. Because remember, all of those sides are congruent, and if I know one side, I can find the perimeter. So that's going to be our goal. When finding the area of a regular pentagon, we need to be able to find two things: the apothem and the perimeter. Once we have both of those, we can find the area of our figure. Okay? Now guys, if you didn't understand this, please go rewatch it one more time. Slow it down, okay? Because we're now going to get to the math examples, and the math examples sometimes can be really short, but sometimes take a little bit of extra work. And there's a lot of things that we've picked up on the past couple months that get brought back to us now. So let's take a look at an easy one. We're going to do number 3. Number 3 is an easy one because they give us all the information. All right, so first off, what type of figure is this? 1, 2, 3, 4, 5, 6, 7, 8. This is an octagon. And every figure that you use is going to be regular. So that means that every single one of these sides are all 10.8. So first thing is my perimeter is going to be 10.8 times 8. So 86.4. Okay? My apothem is already given to me. Now here's one thing that people make mistakes on. This might be given to you, or a length like this might be given to you. Let me change the color. Okay? Notice the difference between the black segment and the yellow. The yellow segment is going towards a vertex of our octagon. That is not an apothem. An apothem is perpendicular to a side of our octagon. Okay? The yellow would also be a radius if we were to construct a circle. Let me see if I can get this. A circle around our figure like this. Let's see if I can get it one more time, a little bit better. Like that right there. So the yellow is a radius, the black is the apothem. Okay? So we don't technically need the yellow to find the area of our octagon. So our apothem is 13. So then our area formula is 1/2 apothem times perimeter. So all I have to do is plug those values into our formula. So as you can see, right, if they're giving us those two pieces of information, life's easy. 86.4 times 13, 1,123.2 divided by 2. My area is 561.6 units squared. Done. Unfortunately, they're not always going to be that easy, as you will see in number 5. Okay, so for number 5, yay, they gave us the apothem. However, we don't have the perimeter. We have to figure that out. Okay, so in order to figure out the perimeter, we're going to see if we can figure out the length of one of these sides. Now here's how this is done. Now remember, each one of these sides in this 1, 2, 3, 4, 5, 6, this hexagon, are all the same length. Okay? Also, the apothem, if I were to draw in 2 radii like so, we now have our isosceles triangle. And the apothem bisects that isosceles triangle. Okay, so again, we know the apothem is 15. Let's think about this. What information do we need in order to be able to find a length of a triangle, or a side length of a triangle? Well, we either need, especially in this case, a right triangle. We either need 2 sides, so we can use Pythagorean theorem, or we need a side and an angle, and we can use trig to find a missing side length. And that's what we're going to have to do. Okay? So, I'm going to bring that circle back. Just like so. So remember, all right, any regular polygon can be inscribed in a circle. Take a look at this central angle from these two radii. Okay? How many arcs are being created? 1, 2, 3, 4, 5, 6. 6 arcs, which means that there would technically be 6 angle measures. So that means that this arc right here is 1/6 of 360. So 360 divided by 6 is 60 degrees. So that arc measure is 60 degrees, which means this central angle is 60 degrees, which then means that this angle on the inside is 30 degrees. So if I pull out this triangle, I know my apothem is 15. I know that this angle right here is 30 degrees. And if I find this, which is this side right here, and they're both the same, I can find the perimeter of my hexagon. So when I look at this, right, there's two options. I could use trig, or in this case, since it's a 30, 60, 90, I could also use special right triangles. Okay, and I'm going to show you how you can do both. Let's look at trig, all right? So the 30-degree angle is a focus angle. The 15 is adjacent. The x is an opposite. So opposite over adjacent is tangent. So the tangent of 30 equals opposite over adjacent. Multiply both sides by 15. So x is going to equal 15 times the tangent of 30. Get my calculator, 15 times tangent 30. That gets me 8.7. So that one side length is 8.7, which means the entire side length, or our B, our base of our triangle, 8.7 times 2 is 17.4. Okay? Now, what if I did the 60, 30, 90? Right? Well, this is my rad 3 side, x rad 3. This is my x side, so I would do 15 divided by the square root of 3. I still get 8.7. So either way, I get 8.7. So now that I know that this side length right here is 17.4, all I have to do to get my perimeter is do 17.4 times the number of sides that I have. So 17.4 times 6 gets me 104.4. I now have my apothem. I have my perimeter. So 1/2 apothem times my perimeter gives me my area of my regular hexagon. So 15 times 104.4 divided by 2 gets me 78.3 units squared. And as I said, guys, these problems can be complex. They're easy if just the information is given to you. It gets a little bit harder when not all the information is given to you. Okay, that's just kind of how it is. Let's do one more. I know this video is a little bit longer, but it is what it is. So for this one, they've given us a side length. So 1, 2, 3, 4, 5, 6. Another hexagon. Nice. So perimeter we can find easily. 8 times 6. Okay. So our perimeter is 48. Done. But we don't know what our apothem is. So that's what we need to find. I'm going to go ahead and draw the center. I'm going to make my isosceles triangle, just like so. I know that this whole side length is 8. I'm going to draw in my apothem. All right. Actually, I'm going to take that back. Before I do that, I'm going to find my central angle. So guys, here's another way. You don't have to draw a circle like this. Instead, remember, the number of arcs is also the number of sides. So to find my central angle, I can just do 360 divided by how many sides my figure has. In this case, it's 60 degrees. It's 6 again. If it was an octagon, I'd do 360 divided by 8. If it was a pentagon, I'd do 360 divided by 5. Okay? Now I'm going to draw in my apothem. And remember, the apothem splits this angle in half. So now the triangle that I have now is 30. I know this is 4, 'cause remember, this side gets cut in half, and I need to find my apothem. So again, I can use trig. I can do tangent 30 equals opposite over adjacent, or I can do special right triangle, and I know it's 4 rad 3, because that's the 30 leg, and this is my 60 leg. So from there, okay, 4 times the square root of 3 is 6.9. And remember, these would flip-flop, so A would be 4 divided by tangent 30. Just double check it. 4 divided by tangent 30. It's also 6.9. Okay, so my apothem is 6.9, so my area is 1/2 my apothem times my perimeter. So 6.9 times 48 divided by 2. Area is 165.6 units squared. I know this is a long video, that's why I'm going to stop there, and we're going to spend an extra probably 2 days on this within class. Good luck.